So
it looks like it's infinity in other directions, so that's a good thing.
Okay, welcome everybody to next installment of our Prague seminar on cohomology. The speaker today is our own Hong Fan Le, our main organizer. I think she doesn't need much introduction. So Fan, please go ahead,
Yes,
start.
thank you. Yeah, Igor. So my talk today is some sense kind of continuation and a complement to the talk by Johannes Nordstrom in May. He say about the Bianchi Massey tensor and rational homotopy type of unconnected compact 8 manifold. And then in last month, Kadeshvili give a talk about A infinity, B infinity, C infinity, and many infinity algebra and the homotopy theory. So now I try to connect on this thing and give some final remark on the A manifold plus some generalization, including some reason we check proof today. Yeah. So the first thing that motivation is a Sullivan algebraic model of unconnected manifold. Yeah. So that is in 77 Sullivan proposal. Algebraic model of simply connected compact smooth manifold. And he used only this data real homotopy type. So I write because usually RTH is the rational homotopy type of the manifold and that can be defined through the algebra of smooth form. And the algebra smooth form is really related to smooth structure and easy to compute. The next thing is a real Pontryagin class. And the real Pontryagin class is a characteristic classes and can be also computed from this algebra, right? And then partial number, that's because everything homotopy is only real, so partial is a number of the n. And he says that's of course there are some finite number invariant of some integral related to this real homotopy type R and N. And then that is you have the diffeomorphism time of the N and here and the map here that is a subject is a only finite number. The number is a finite. So that's a most of the diffeomorphism time of the N can be recovered from the algebra smooth form and the torsion number. Yeah. And there's a map and
Peter asks in the chat. I think piecewise linear forms are fine in Sullivan's work. Is it?
Yeah, so I might say the real homotopy type. So I can ask the next thing I want to say. What he proved more is a rational homotopy type of N by N. Is equal just the space of the piecewise linear form. Yeah, and divide this to the differential graded commutative algebra. Equivalent. So equivalent is a zigzag quasi-isomorphism. That means a quasi-isomorphism. That means morphism and the inducing isomorphism on cohomology, right? So that's a con zigzag. And more or less the same thing. That's a real homotopy type. is defined by equivalent classes of the differential form. That is a differential graded commutative algebra on the equivalent. And that's a must, how to say, things that makes Sullivan theory popular, because before Sullivan modern there only the Queensland modern, and then there several other modern, German modern, yes, that in the book by Tandra. They consider, but somehow Sullivan modern is the most popular because they have the minimal modern. I shall not describe what is a minimal modern here. That's a minimal modern of, that means that's a for of not only space of the piecewise polynomial form or a smooth differential form, but of any differential graded algebra, yeah. And then of the unconnected, yeah. And some finite net, maybe that's a cohomology ASCR is a finite or a dim. And this is a modern, that means that's a algorithmically computable. So you can think it's like a group no basis. Of course, I don't know that's comparison is okay or not, but using such kind of minimal model, you can prove a lot about the geometry topology of manifold. And then the book is a very good book. That's a book by Felix. Felix Hunterin and Opera, sorry, that is Opera. There are many people working on the field, and Felix Opera and Tandra. So that's the second algebraic model in geometry. Very good, very good. 2000 13, yeah. I forgot each year. 2000, maybe that noon 8. I could not remember exactly the year of publication, but as I consider a lot of the application in the geometry of symplectic manifold, group action, and Lusternik Schneermann category thing. So today I shall not discuss about this thing, and I say that's what's it using minimal model you can do in sense of law dimensional geometry. So that is why I put the Python name is dimension 8, because of we are like Johannes Nordstrom. He was motivated by geometry of the G2 spin 7 manifold, yeah, and that is dimension 7 and the dimension 8, and the same is the dimension. That's what is a node. That's a first. That's a Miller in 78. He proves that's a error -1 connected compact manifold MN of the dimension less than 4 error -2, and the error is bigger than equal 2 is a Forman. So that is if error equal 2, so dimension here is 6, yeah. So that's a long time team Crowley and Nordstrom. They put the paper in archive in only 2015. was published in 2020. So I take this year after publication. They say that's the extension. The error -1 connected manifold. Also, that's a compact of dimension n less than equal pi error 3 is determined by that's a Cohomology ring. It's a rational coefficient because he says that what is a rational homotopy class, and the summer class they call that Bianchi Massey class. That is you can think that in the degree 4 in symmetric class of symmetric of the H of the M of Q. So it looks like a Bianchi tensor. There's a Riemann tensor of degree 4. Yeah, so that's why it's a Bianchi. And Massey because it came from Massey triple product. So if you remember, that's a your Hannet Nostrom said in his lecture in May, that's he tried to tensorifying Massey product, and they got that notion. So and then very recently, and that's also that's a Nagy Nostrom in the put a paper in the 2021 in archive, and they consider one dimension more because is and equal to that here dimension 7, that G2 manifold, right? So what is happen is a spin 7, that dimension 8. Then they say that the following thing. Error -1 manifold connected, connected, and also everything is a compact manifold of dimension n and less than 1 dimension more. Error 2 is a Farman, so they can only prove that is a Farman if and only if that's a how to say Bianchi Massey tensor equal 0, because that is something related to Massey triple product. Is that okay? And the other thing is a pentagon Massey product. So that is also come from Massey for product, but the instead of ribbon, then you consider also product, so that you go to pentagon, that means 5, because equal 0. So that's some new thing. So that's what you can obtain from the minimum model by Sullivan. Now I go to finish the first part, Sullivan algebraic model. Now I go to the second part, that's a host homotopy. And the host homotopy is an Unital C infinity algebra. So that is begin from our work. It's Fiorenza, Kawai, me, and Schwarzhofer. In 2021, of course, he put the archive paper in 2019. And then he proposed also this host homotopy, and in our recent paper, we make a little bit improve such a structure, not only C infinity algebra, but Unital. And Unital makes a computation much simpler. Yeah. So what is a host homotopy? So to define a host homotopy that you need Poincaré differential graded commutative algebra. Yeah. And that's what is a Poincare differential graded commutative algebra. You know that's a compact manifolds and you have a Poincare duality. Poincare duality on the homology. Yeah. So that's you have the homology, and then you need some element of fundamental class. That means that you define first fundamental class. That's a element in the H and of degree and that highest degree. So that's a and of E. That's an element. So linear functional to the field of K. Yeah. So I consider everything over K. That is a field. So that is a top degree. And then you know that it's a success. The cut product is a non-degenerative. So that's a modern is a cohomology of compact manifold. Success alpha K beta L equal. So here like integration, but that is a just nothing else like fundamental class beta L if K plus L equal N and equal 0 and yeah. And then what is interesting is that you can extend this product to the whole differential graded commutative algebra. So they extend that pairing to A by setting that AK BL is it's the same integration, but now I take the cohomology class, yeah. BL. Yes, because pairing define homology, cohomology, yeah. If K plus N equal N and 0 ends. And he says that this definition, that's this pairing is non-degenerated if the pairing is non-degenerated, yeah, degenerated. Then the Poincare differential graded commutative algebra is called non-degenerated. And that seems that every time you have some non-degenerated bilinear form, you have extra structure, right? And then at the that is a Poincare algebra. That's the extra structure here. Compatible is a host homotopy. Yeah. So now I give the definition. So let I star D that multiplication here and the pairing is be Poincare differential graded commutative algebra. Sorry? Yes. Sure. Everything is graded, yeah. Yeah. So then host homotopy. Topy is for this our A, E, and the pairing is operator of the degree -1 from A to A minus.
Could you please define the,
1.
Could you please define this?
Some question?
Yes, so I have a question. Could you please formally define this Poincare differential graded commutative algebra?
Sorry, Poincare differential graded algebra.
Could you please formally define Poincare differential graded commutative algebra?
Yes, it defines that a Poincare differential graded algebra. That means that the first I define the Poincare duality on homology.
Yes.
And then I extend this pairing on the differential graded algebra by this formula. Pairing of these two things is a pairing of homology class. If it has the right degree.
And why it's
Because,
commutative? Why it's commutative?
That's the definition. Then you check that is define some pairing, but it may be not how to say on the homology is a non-generated. But you have example. Please check our paper. It's a Fiorenza, Cavai, and Schwachhofer. You have example of the Poincare differential graded algebra. It's a degenerated pairing, and admit no host homotopy. So that is
the question was about the term commutative. Is it commutative in the sense of graded commutativity?
commutative.
Yeah.
Sure, I think it's a graded commutative.
Thanks
Yeah,
for-
because is that your question, Roman?
Yeah, this was my question because it doesn't
Yeah,
look
yeah.
to be just
Yeah,
commutative.
sure. Everything is a graded commutative.
So it's super commutative, yeah, in
Yeah.
physics. No, it's synonym. Okay.
Yeah. So you're working on graded geometry, yeah, and the algebra. So that's a host homotopy is you define some operator of the degree A B minus here, and satisfy the following condition. That's a B square equals 0, and then D minus on D minus on is equal D. So it minus E. So here acting like an identity, of course, and another one also D and D minus on and D here is equal. So you consider here like an identity. So that's okay B. So that simplify many computation, and the marks answer that's a PH definition equals that's a identity of the A minus a commutative of D and D minus is a projection. And then you have the so-called orthogonality condition. So that means that in D also in D so equal 0, and then in of the pH of the D minus is also equal 0. So we have a lot of kind of orthogonally computation, and this simplify a lot of computation. And the example is D minus. Here everything is a D minus. Yeah. What is your question, Dennis? Yeah, minus 1 because that, yeah.
And the minus by close to D is also minus and not minus 1. You have D minus square, and then you have D minus D minus, and not minus
notation
1.
for D minus.
Yes, and I see 1.
Each notation.
So
I see some 1 behind the minus. Yeah, but it is not inverse. It is just pseudo inverse.
Below?
No.
Yeah.
Up, a bit up,
It's-
up.
Yeah.
And a bit up, please.
Here.
And right.
Here.
And here
Yeah.
I see D minus 1, yeah, but it should be D
No,
minus.
a minus.
Okay.
Everything is a minus. Zero, no minus.
And
one.
also
Sorry,
there, yeah.
because not
Inverse
inverse.
needn't exist.
It's
of course,
only
because-
everything is a minus.
Okay.
but it is
because
like this
in the
Penrose
case-
pseudo inverse. Sure, yeah.
So that's only not invertible. Yeah, I don't. If you take the minus 1, that you ask for invertibility, and I do not
Yeah.
ask any invertibility. Yeah.
And second last line is also D minus 1. That's also a type.
Yeah. So that of course that is a typo, yeah. So I do not say anything about the invertibility, and that everything is a minus. Yeah. So so then the example, of course, that's a Gram complex. That's more than that. In our paper, I think that's a Fiorenza Zakavai and Schwachhofer. We have the example of the quite a lot of exotic example. That's what you need in our case here is I think that I should use it on is our Gram algebra. And for our Gram algebra of the smooth compact manifold, and that is certainly that d minus 1 is how to say decomposition of the green operator example. So that is we have the and we have the d, we have the also that is z pairing is natural because and the d minus 1 d minus, and I only say that is equal that green operator composition green operator, that's green operator in this way, that's the inverse of Laplacian, and the composite is d star, and that is working example, and for exotic example, like take
Relying on compact manifold.
Yeah, sure. Everything compact manifold, therefore you have Poincare duality.
Okay, and the inverse of the Laplacian.
It's a green operator.
So if it has a kernel.
That is you have to define on the it's
inverse on the complement of kernel.
Yeah.
It is inverse on the complement of kernel.
You consider
Should be,
only
I guess,
complement,
on the image.
Yeah. Thank you. Yeah, that exactly. That's such kind of operator only used by Merkelov, but he never much on the how to say notion of host homotopy, So that is a Merkelov paper on the user circuiting. Okay, so then
So when you take the bracket of D and D minus.
Yes.
So what is the total degree? The total degree is.
Total degree is one is plus, one is minus, degree 0.
Okay.
Right. Therefore, that like a projection. Yeah. Then what is a minor theorem? That is a theorem is a following thing that is only our paper in 2001. That is a let error bigger than equal to a minus 1 is error minus 1 connected Poincare differential graded commutative algebra of degree n. If I admits host homotopy, then zero exists non-degenerated. Right. And a very important finite dimensional Poincare differential graded commutative algebra. I denoted by Q, and that also admit host homotopy, and therefore you have the D minus here. Success to D is equivalent to A. So in principle, that means that could be considered like a differential graded algebra model instead of Sullivan model. Sullivan model also very good, but not has a different property. So if you wish to work only differential graded algebra, you could choose this one. But we choose C infinity algebra. Yeah. So the next thing I should talk is
Homotopy. When you define the pi projection, the bracket between D and D minus, that's the graded bracket, right?
yes.
Yes, of course. Yeah.
So everything here is graded. Okay. So now the next thing is what you do, because it has if you remember in the Kadeshvili lecture, he thinks that's how he tried to construct homotopy equivalent between homology of the differential Gray algebra and the differential Gray algebra, and something completely not happens. Therefore, he had to modify, and this way he get, how to say, A infinity algebra. And later on, he noticed that in the category of the field over Q or R, he could work on the differential graded commutative algebra. So now we consider the following thing. So we have our concept in that paper. You concept is small model because it's a finite dimensional, yeah, and very good. So we consider also homotopy, transfer PHK to H, and D equals 0. H is a, how to say, projection of this operator. So that H, that harmonic element is a PH here of the A. Yeah? So that's a the Hodge homotopy defines a harmonic space uniquely. So that's in our paper is 2021. You emphasize on the harmonic space, but actually the operator is more important. So in this our new paper, you emphasize on the operator equals that a Hodge homotopy, and then we look at the operator D here. D minus here, that is satisfies the condition of the homotopy transfer theorem, yeah. And moreover, it satisfies the following condition. You can check easily. That is PH D minus 1 equal 0, and D square is 0, and D minus of the 1 equal 0. 1 is a unit, yeah. So notice that here's a differential graded algebra. Differential graded commutative algebra has unit, and this unit is satisfies the property is what is a unit. Of course, it's a unit of the unit element in the commutative algebra with multiplication. Yeah, so that's a unit, and then D of the units is also equal 0, and the conditions that's every time you have the K bigger than over 3 apply to many elements in it, but if you have some 1 here, then everything also 0. So see the condition simplify a lot of computation, yeah. So that's you have this condition, and then by Gessler theorem, the resulting C infinity algebra is Unital, yeah. So Unital is the following kind. So that's this last kind of the observation we did only in our paper is Fiorenza checked recently, and this simplify a lot of computation. Now,
The unit is just the
Unit.
identity function. So the unit function.
Yeah.
Okay.
Yeah. So
So every manifold has a unit function.
Yeah.
So that's
now,
Sorry, just one question about the same thing. So the condition that mk vanishes when one of the arguments is 1 applies only to k greater than 3, and when k is equal to 2, it behaves.
so that's of course that's M2 of the 1A equal M2 of A1. Yeah. So that's a unit
Okay,
of
so
the multiplication. Yeah. So that I already said, but I didn't write here. Yeah. So that is a kind of very obvious condition. Yeah. So that's now that I state our theorem. That's a
sorry. Just again about the units. So in what cases would you encounter these models without a unit?
So that's why we didn't consider any exotic example. So that you only consider some exotic example. Consider differential Poincare algebra is a non-degenerated.
But
Comparing in our paper before, but in our last paper, you consider everything is standard. Yeah.
But any such non-unital models would not correspond to manifolds. There would be some other topological spaces.
Maybe non-compact.
Yes.
Yes, of course, not
Yeah.
compact.
Duality, that's why we use a Poincare duality. Yeah. So that's a non-compact, you don't have Poincare duality. So that's of course you can do more because on this thing you can apply to our bphone and the more. But for simplicity, you consider manifold. Now that's now I state that theorem that we get it's Fiorenza recently. So let bigger than or equal to A star is R minus 1 Poincare differential graded commutative algebra of degree n. Admitting a host homotopy. So if n less than or equal to R at minus 1 plus 2 and bigger than or equal to 4, then okay, so that's a check. Then H of the R carry minimal unital say infinity algebra. It's making algebra making it say infinity isomorphic, quasi-isomorphic to original H such how to say minimum, that means B1 equal M1 equal 0, yeah, and M2 is a multiplication on the algebra standard, and then M K equal 0 for K bigger than L minus 1. So here L. So that is our main theorem. So let's see. That's I already finish this, this.
On the board just to show the full theorem. Okay, so can you just comment again on these constants R and L and the relation to the dimension?
So that's n. For example, the following thing, n equal 4. So error equal error equal. So example. Yeah, so in particular, yeah, in particular, yeah, in particular, n k because pi equal 0 if n less than equal 6 error minus 4. So error equal to 6 error minus 4 is 8. So you come to the dimension 8. Yeah. So that means dimension 8 has the armed multiplication beginning from 5 equal 0. So only 3 and 4.
Just to clarify, so again, can you show the hypothesis? So R is the hypothesis on.
Connected. Sorry.
Okay. So R is a connectedness condition.
Yeah.
Okay. So
connected condition of degree n. Yeah. So that meaningful.
degree is the maximal degree if you have non-zero chains.
For example, R equal 2, that means simply connected. Simply connected, and in dimension, here 6 error minus 4 is equal 8. Then we have such a thing, yeah. And then the next thing, that's
Sorry, and what is L?
L is any number. Because
L is any number.
So now that's the next thing. That's how it recover on the result before that, because the dimension is our original condition. That remember. Sorry. Each question.
Go on. Did you have a question? Okay, maybe.
Yeah. So that's so that dimension 8 now it considers if you have the dimension where you have the only 2 non-trivial operation. Yeah, that M3 and 4 because M1 equals 0 and 2 multiplication. You ask what's next. M3 then go down again. MK becomes 4 equals 0 if n less than equal 5 and minus 3. So that is you go down to the reason by Crowley and Nordstrom, and actually our reason they use a little bit different. So that's actually our previous reason is a theory Zakavai and Schwarzhofer. Yeah, so that's we proved in our paper the following thing: if dimension less than equal n minus 5, for example, dimension 7, go one dimension lower that T2 manifold, for example, then that if there's only one operation M3 dimension, of course, it goes further. Dimension that's MK bigger than equal 3 equal 0. If they go to the dimension 4 error minus 2. Yeah. So you notice how to say the rule 4 over minus 2. Next thing you go to 5 error minus 3. Next step go to 6 error minus 4. Yeah. Every time you plus error minus 1. Error minus 1 is a connected component.
So just to clarify, so the theorem states that for say if n is some large dimension.
Yeah.
Then L is the kind of the measure of the number of non-trivial products that you have.
Yeah, I say that, but not really. Of course, our reason using setting, that's so also prove it. So he puts his paper 2 months after he puts a paper in our archive here, and actually he also proves such a theorem using just only homotopy transfer by the Kadeshvili. And his computation very complicated, yeah. And therefore, of course, he also gives the same reason, but I should say in the last part, what you can prove, he cannot prove. Yeah. So that's actually the first proof by show, and then you use our method to give much simpler proof of the show result. So that's so now yeah. A degree. So that's a degree is a 2 minus k. Yeah. So so I only finish this part. Unital algebra. Also homotopy. And this part is actually that you can finish immediately because that is a consequence of the conditionally reason, and he just gives the talk 2 weeks ago. So that's once you know the homotopy type of infinite algebra, you say about the homotopy type of the underlying manifold. Yeah. So that is a theorem statement also for real homotopy type of the manifold. So now I shall say about the Bianchi-Massey tensor and Harrison cohomology and formality. And the this part is a show on so didn't know about it because he knows and want to get analyze the Crowley and Nordstrom result. So so I only this recall that Johannes Nordstrom says that Bianchi-Massey tensor is the way of tensorifying the Massey-driven product. Yeah, so that is an abstraction to formality. And then and moreover, in dimension 7, this is defined together cohomology ring, the complete homotopy invariant of manifold. So so what is the counterpart in our C infinity algebra? So that is our theorem. Is the Fiorenza. So for you take the for C Unital, yeah. C infinity minimum Unital minimum C infinity algebra. Obtain it by from our obtain from a host homotopy from host homotopy. You can construct the operator M3, and operator M3 is a linear functional from the tensor of the how to say of the 3h go to h of the degree -1, yeah, of -1. So it can be considered as a Cauchy complex, Cauchy chain complex, but that is it satisfies certain conditions. So that is a Harrison cochain complex. So that you can define element 3 in the Harrison cohomology class of the here 3 and the -1 here. It's a homology algebra n. Is a value in the same cohomology, such as Z and 3 does not depend on host homotopy. So that is therefore it's a homotopy invariant, yeah. Of manifold. And the second thing we show that M3 Z cohomology horizon class and Bianchi Massey tensor define each other uniquely. So that he translated the Bianchi Massey tensor in terms of the Harrison cohomology. So in class 5 minutes, I should say about the final remark, how it's related to a manifold and generalization. So that's mostly I say about the dimension and the some condition and the higher operation on C infinity algebra vanish. So one can ask us that if you have another condition in this dimension, can you get some more information on it? That's very natural. And the prototype of this theorem is a Cavalcanti. For example, Cavalcanti proves the following theorem. So that he proves that R-1 connected compact manifold of dimension 4R is BA equal on is formal. So look, what is the improve of the Miller? Miller says that 4R minus 2.
The Betti number?
Betti number. So Miller says that the dimension less than 2, then it's a formal. So you can increase dimension 2 more. But so you put condition on the Betti number, then it's also formal. So that's a proof. Actually, that is a zero conjecture, and you prove it. So that is zero conjecture, and proof today. By Fiorenza and myself. That is the following theorem. That is a generalization of this theorem. R-1 connected a manifold compact also n dimension less than equals R. R minus 2 plus 2 here. So I increase dimension on 2. Is formal if B are equal 1. Yeah, so that's a general natural extension of the Cavalcanti theorem. Yeah, so of course there are a lot of more theorem. For example, you can put another condition, or you can look at the famous Deling, Morgan, Sullivan theorem on the formality of Cayley manifold, because you have the two commuting host homotopy. So that you think everything in the term of the operator, then you I also have some conversations with some guy, but they say that they try to prove also formality of how to of the conformal symbolic manifold of Weissman type. So that means if you put some geometric condition on the manifold, then you may have some formality or have some restriction on the C infinity algebra. That means that homotopy type. Yeah. So I finish. Yeah. Geometric condition, for example, that is already in the Merculo paper. He tried to reprove the link Mumford and Sullivan formality theorem for Cayley manifold using C infinity algebra. Yeah. So but he did not interpret it in terms of the two commuting Hodge homotopy, but you can interpret it in that way. That you have the two commuting Hodge homotopy, then you get the formality in that way. Of course, maybe that not only, but at least that's you make such interpretation. So that's Sullivan and Belling and Morgan and somebody else, 4 people. Yeah, I remember only Sullivan, Belling, for Morgan. Yeah. Morgan, yeah. So they say that's main things like emphasize on DDC lemma. So DDC lemma, you can consider that yes, some operator has you can also interpret it in terms of the commuting operator, maybe. But that is how it's better to think that you have a lot of kind of the commuting structure and a lot of operators, and you can compute computers. That's a hard, so because how to prove the theorem, you just compute the operator and McKay in high dimension, and using the Consivic-Soderman 3 formula, root formula, yeah. Root formula, how to compute transfer structure. And then you see that you use only this operator, the homotopy, yeah, multiplication. And so that means that because our original structure is a differential graded algebra, so you have the only non-trivial operator that M2 and the D. So that's you have two operators, and you have the homotopy is this B minus here, but B minus here satisfy a lot of property, and therefore using the Consivic-Soderman formula, everything very simple. Everything is how to say. Of course, that using also the conditions that Unital because of the degree, yeah. So Unital says that a certain degree is a contributed nothing. So it takes a degree only higher, and degree higher, you have only finite combination, yeah. So try to check few formulas and you get everything. So that is very simple and short, yeah. The proof.
This is interesting. I'm by no means expert in this area, but Cavalcanti was interested in topology after he did his work in generalized Riemannian manifolds, generalized complex complex manifolds.
Yeah.
So he sometimes assumed that the manifold admits spin structure and these such spin structure in his topologic papers with Galtieri. And here it is not assumed. No, in this theorem of Cavalcanti, you assume just the Bethe number is 1, the earth Bethe number.
Yes.
The compactness, if I remember well, of the manifold.
Yes, I think that's the Cavalcanti also use the compactness, because actually they use of course when they prove something they use on the Cavalcanti paper they use a new concept by Fernandez and Muno. That's a K formality. So the formality you can think is the following way: that a manifold is a Poincare dimension. So that half is everything defined by half dimension. Another dimension is symmetric. Yeah. So that means that they meet the formality because Sullivan minimal algebra is defined. I say that algorithmically. So it consider the dimension higher and higher. So that's they say that for Poincare differential graded algebra, you need to only prove that the formality is the half dimension. Then you prove everything. Yeah. So that's a Cavalcanti use such a thing. Therefore, he use a minimal Sullivan theory plus this new observation and theorem by Fernandez and Muno case formality. And then he constructs, see that what is a modern and each dimension. But second thing, that's of course at least show and demonstrate that using even a normal homotopy transfer, he can only prove something more. But he, because nevertheless quite a complicated computation, so he makes a conjecture about the generalization of Cavalcanti, and he could not prove. And then you see that it's our simplification. Yeah, using the Hodge homotopy, you can prove it very easily.
Yes, thank you. Is it his recent paper of Cavalcanti or not?
No. I mean that's
No,
a
it's
very
old.
long time ago. That's if you have some new paper by Cavalcanti and he discussed about the formality, then please send me later.
Yeah, thank you. Thanks.
Yes.
So if I understand correctly, the main tool that you're using in these results is this Hodge homotopy. So and you showed that you can construct it for compact manifolds. But I'm thinking for non-compact manifolds, could you do something like first do a homotopy reduction to some compact space, and then study the model of that compact space?
Good idea, but we have not yet considered. Yeah.
But if you do like a regular homotopy between manifolds or topological spaces, how does it transfer to this algebraic model? It's just a homotopy of the algebraic structure. So if on the geometric side, you have an explicit homotopy between manifolds.
Yes.
How does it show up in the algebraic model?
Algebraic model. So that's so you know that's a theory of Sullivan. Yeah. Sullivan that only the theory that if the homotopy equivalent, then it induces a homotopy between the model.
But would that homotopy have any special properties? Like because you asked for of the Hodge homotopy, these extra properties.
Yes.
So if you just have like a homotopy retraction.
Because of it have not considered that thing. Yeah.
Okay. All right. Well, the thing would be interesting extension.
Yeah.
Okay. Thanks. More question? Yeah.
Okay. So if Poincare
you mentioned that in the close result, sometimes
so that's if the manifold admit that differential graded algebra admit Hodge homotopy, of course that's not unique because for example, even on the metric Riemannian manifold, it's very metric. You have a lot of the Hodge harmonic space and
for a given D, because it's not linear parameter because of the quasi-inverse condition we cannot rescale.
Yeah, so I actually that's when you did work with on the 4 people, you try to think a lot about our kind of the small quotient algebra. Yes, that means that's what you can get from here. But we have could get a very small version. So we stop to think. But that of course that's I don't know. So that I mean that's of course you add some more homotopy type, then it's a really geometric structure. Yeah, that's a really geometric structure.
Yeah, because, so your aim to find it independent. It's also find a dimension of each. So the rate of the Cohomology is minus.
Yes.
Is n-1.
Yes, yes. So that is considered like a inverse. Yeah, one side here and goes here, go back. Yeah, yeah, yeah. Yeah, so this is a very simple, but if you look at the example, yes, then you see those for the regular manifold, then it's a very simple. But
Quite seamless.
so everything here there, nothing -1 because I don't, yeah. So everything is a minus. I don't ask anything about invertibility. -1 is because I forgot, and that means degree -1.
You get a bunch of project services in the set of all which
We have not yet considered such a question. Of course, that could be interesting. Yeah. So we try to think a lot of things that our kind of finite dimensional, non-degenerated Poincare algebra. It has all the property homotopy equivalent to the original algebra. Much very good model. Yeah. But then yeah, it spends some time, then gets a very written result. So only reducing to C infinity gets something more, yeah, interesting.
Okay. Are there any more last questions? Okay, doesn't appear to be the case. So let's thank Pan again and
yeah, so yeah, thank you.
okay.